This is Mr. Potter, and welcome to day 13 of our logic curriculum. Today we're going to be talking about two-column proofs under two different situations. One, where we're using Theorem A to deal with conjunctions, and the second is how we actually prove arguments are invalid using proofs by contradiction. So we're going to start with how we actually deal with conjunctions using Theorem A. So we're going to do a real quick recap on Theorem A. This is on page 23 of our textbook. And the idea here is that if I have a conjunction of two statements, it's going to imply the first statement. Now, in reality, whenever I have a conjunction of two statements, a conjunction is a statement that is only true if two given statements are true. And so if I'm saying that the conjunction is a true statement, then certainly the first statement must be true. And in fact, even though we don't say it on page 23, the second statement has to be true as well. So the idea here is when I'm doing a two-column proof and I see a conjunction, I can actually break it up into the two components and use Theorem A as justification for it. And so I want to do a real quick example of a proof like this. So in this situation, Barney likes to bowl and Wilma has red hair. If Barney likes to bowl, he will go bowling. If Barney goes bowling, he will take Fred bowling with him. Therefore, Barney will take Fred bowling with him. You may notice something about this little part here. We're talking about Wilma having red hair, but that's only mentioned in this statement. We don't use Wilma in any other part of this. So Wilma is almost like it's extra information, but we're going to still use this in a proof we're going to talk about in just a few minutes. So my first statement says Barney likes to bowl and Wilma has red hair. So that's a conjunction of two statements. We'll call them B and W. For the second premise, we have if Barney likes to bowl, he will go bowling. So we'll have B conditional G. And then for my third premise, we have if Barney goes bowling, he'll take Fred bowling with him. So that would be G conditional F for Fred. Therefore, conclusion, Barney will take Fred bowling with him, which is just F. And so the idea here is that because I have this conjunction, I'm going to need to break it apart so that I have some pieces to use with these conditionals. Otherwise, without these terms from this conjunction, all I have are conditionals, and the only thing I could do would be a hypothetical syllogism. So I have my argument here. I have B conjunction W. I have B conditional G. I have G conditional F. And then a conclusion of F. So I'm going to do my two columns, statements and reasons. And I'm going to list my premises. So I've got B conjunction W. I've got B conditional G. I've got G conditional F. And these are all premises. I mentioned that whenever I have a conjunction, I can use Theorem 8a to break it apart into its two components. So using Theorem 8a on statement 1, I can say B conjunction W implies the first statement, B. And I'm more than welcome to say it also implies W. And Theorem 8a is one of the only theorems that we have that can use a statement twice. And I mentioned that this statement here is kind of extra information. We're not going to use W anymore in our proof. Notice it doesn't show up in any other premises. It doesn't show up in our conclusion. So it really is extra information. But now that I've used up step 1, I need to put two statements together. I can either put 2 and 3 together, because that would give me a hypothetical syllogism, or I could put statements 2 and 4 together. B conditional G and B. So if I do the conjunction of two and 4, this is a modus ponens situation. And that's going to give me just plain old G. But G is not my conclusion. F is my conclusion. So I need to continue. Of course, at this point, I've already used up statements 2, statements 4, and statement 6. So the only statements I have left are 3, 7, and this bit of extra information, which I'm not going to use. I know that I can put 3 and 7 together, because that also is modus modus ponens. So I could say G conditional F conjunction G. That's the conjunction of three and 5. And modus ponens gives me just F, which is what I want. Which makes my argument valid. So again, notice that in order to deal with this conjunction, I had to break it apart into its constituents. I'm not necessarily going to use both parts. I may only use one part, but I have the option of breaking it up into both of its parts. And that's important to know, especially for those problems who are going to be working problem number 41 on the homework assignment, which I'll talk about in a later video. So the first half of today's lesson was dealing with conjunctions. And whenever I have a conjunction, I need to use Theorem 8a from page 23 to talk about that. The second thing that I want to talk about today is I want to deal with proofs by contradiction. Earlier I stated that a two-column proof is a more concise way to prove an argument valid. There are some very rare situations where I can use a two-column proof to prove an argument invalid. And here's one example here. If February has 29 days, then it is a leap year. If it is a leap year, then there will be a presidential election. But there is not a presidential election. Therefore, February has 29 days. So I'm going to list my premises. My first premise says that if February has 29 days, then it's a leap year. My second premise, if it's a leap year, then there will be a presidential election. My third premise is that there is not a presidential election. Therefore, and this is the conclusion I'm trying to reach, February has 29 days. So given these premises and trying to reach this conclusion, I'm going to list my statements and reasons. I've got F conditional L, L conditional E, and negation E. And these are all premises. And I'm going to go ahead and put statements 1 and 2 together because that's a hypothetical syllogism situation. So F conditional L with L conditional E. This is the conjunction of 1 and 2. And that should give me F conditional E by using hypothetical syllogism. Of course, this is not my conclusion, but I've used up statements 1, 2, and 4 to reach this point. So I still have to put 2 statements together. So I'm going to put statements 5 and 3 together. 5 comes first because it's the conditional. So this is the conjunction of five and 3. And this is a modus tollens situation because this is the negation of my conclusion. And so I reach the negation of my antecedent. So I reach negation F by modus tollens. This is a problem, though, because I've concluded that negation F must be true. But I'm trying to prove that F is true. I've proven that negation F is always going to be true. But I wanted to prove that F is true. And so that means if negation F is a statement that's always true, F must be a statement that is always false. And so that means that we're dealing with a contradiction. You may remember from an earlier lesson that a contradiction is a statement that is always false. And so in the course of a 2-column proof, if I end up proving the negation of the statement that I'm trying to prove, that allows me to say that this is an invalid argument by a proof of contradiction. In other words, I proved the exact opposite of what it was I was trying to prove, and therefore I've reached the opposite conclusion. So, 2 main ideas for today's lesson. One is the use of Theorem 8a to prove using conjunctions. Whenever I have a conjunction, I must break it apart into its 2 components. And the other part of today's lesson is I can use a 2-column proof to prove an argument invalid. But the only way that I can do that is by using a proof of contradiction. So once again, I thank you for watching. This is Mr. Potter. See you later.